Checking voice. Welcome, this is our beginning video into linear algebra. I had filmed a couple lessons for this online class that had started in spring of 2025, and did not record videos for the review unit, which I refer to as Unit 0, so that way there's no confusion with the textbook. Since many students can kind of come in with varying levels of understanding when it comes to vectors and matrices, I wanted to make sure that those students had an opportunity to listen, at least from me, if I'm still your instructor, whenever you take this course, if they reuse these videos or not, or if you found me from the YouTube channel. And so I just want to make sure these are there. Many students, before they take linear algebra, you would see vectors and matrices, whether it's in physics, whether it's in Algebra 2 is typically the first course you see matrices in. And then really, if you, depending on your curriculum, you may have taken a multivariable calculus, a Cal 3, or even in Cal 2, you really start to see two-dimensional vectors, and then multivariable, easily see three vectors. And many of the operations and things like that you may have seen before, and so these videos are more so for the people that have not had that foundation. I know at the high school here where I teach at Mount Vernon School, students can take this course, which is a prereq in first semester of calculus, and so that's why, again, I want to kind of have this intro video. The textbook that I'm kind of using here is really to kind of base these videos off of, and then the future videos, I'll hold this book up as well, as the No Bullshit Guide to Linear Algebra. If you're in my course, you'll see that listed under the resources. The other text, which if you are in the online course, you have a copy of, is the Introduction to Linear Algebra. This is the main organization of the class that we'll kind of follow. But to get us started, depending on your background, you may or may not have heard of the word vector before. If you've ever seen Despicable Me, the famous villain Vector, because he has magnitude and direction. Many people have, a lot of students have that, and if you haven't seen that movie, since it's kind of old now, I highly encourage it. But it's where Minions essentially started from. Vectors are really used in many different courses, fields of study. It's not just a mathematics thing. Again, if you've ever taken physics, vectors are very important in physics. And the primary reason why they are so important is because they can be used to describe forces, motion, the direction that something is moving, velocity, acceleration. Because when we think about vectors, primarily we think about them in terms of a coordinate system. We'll kind of call this the x and y axis. Let's kind of continue to use black here. If I start my vector at the origin, I refer to this as the starting point or the initial point. A vector describes how something is traveling, the displacement, essentially distance traveled as long as it's positive. I guess really displacement. Between this initial point and some terminal point, which I'm just going to place here, some final point. And so the word vector is essentially describing the path, the straight path from this initial point to the terminal point. And thus, when we describe vectors, we can essentially describe vectors as having some kind of known length or magnitude, and then some known direction, because if I was to draw this arrow is very different from if I started here and went straight down. And one of the final videos, because I'm going to try to break this up into smaller chunks, I'll kind of describe this or kind of discuss this a little bit with another example that we'll kind of see naturally arrive. And so vectors, it's really important that when we were talking about vectors that we were paying close attention to not just the arrow itself, but its placement. Where its initial point is, where its terminal point is. And typically, again, this is what students are familiar with. They view a vector as an arrow. They view a vector specifically from physics, where again, I have this vector, and I was going to use different colors, where I can describe this vector in terms of its components. which we look at in terms of a right triangle. It's why trigonometry is so important before you take physics class and really linear algebra at its core. Because I look at this in terms of a x component, which I'll label as v sub x, and then some vertical component, which I'll label as v sub y. And I can denotate it in terms of its components, and this is known as component form. I can say that v is equal to vx dy, describing this. And so especially when we're in this rectangular coordinate system, this Cartesian plane, we can view a vector in terms of how far to the right and how far up something has traveled. And again, if you take in physics, we are aware that our horizontal and vertical motion are independent. It's why we want to describe this in terms of those two independent pieces or those components. Because if something was to travel a certain distance to the right and then a certain distance up, that will always create the same kind of arrow. Again, once we start placing this on a grid, depending on where I place these arrows, the arrows may not be equivalent. And so it just depends on if we care about our starting point or not. And we'll discuss this more later. Now, where this course, I think, becomes, linear algebra as a whole, becomes probably a major game changer for students because the AI field and computer graphics and computer software and programming is that vectors can be found in all of those places where when I define a vector, we're not necessarily defining then certain motion or certain directions like this. And so a vector can also be defined as a list of items. We essentially say a set of items, some kind of ordered pattern. So like a first component versus a second component versus a third component. When an item is in that spot in the list, it has a specific quantity or name attached to it. If you've ever worked with spreadsheets and you create a function, if you think about each little piece of that function that you have to use means something or tells something to the computer, well, you're essentially creating a vector. You're creating a 3-dimensional, a 2-dimensional, a 4-dimensional. Just depends on the number of items in the list. Well, mathematically speaking, we want to focus more in terms of the vector algebra and specifically the linear algebra pieces. And so we're going to more strictly focus in what we can see and think about vectors more in terms of these visual representations, but just know that they do represent things outside of just did something move from point A to point B, or how quickly did something move, or how quickly did that rate change itself, and that it can illustrate many, many other different things. Now, what I have up here is what we refer to as a 2-dimensional vector. And once we start getting into the structure of the class, this word dimensional and dimensions is going to play a greater role, where when I'm graphing something like this, the 2 dimensions are specifically referring to the x-axis and the y-axis. I have 2 measurements that this vector is essentially living in. I have these 2 components, right? There's no coincidence that those 2 things are the same. And if I'm looking then at essentially the entire plane here, this entire board, this entire x and y axis, if I was to extend these out infinitely, if I was to look at this space, we refer to this space as R2. It's the set of real numbers squared because I'm looking at all of the ordered pairs in this real space. And something that we'll discuss a little bit later is that if I want to talk about all points in this space, we can describe that using vectors, another really important idea of linear algebra and something that kind of review a little bit towards the end. And so again, when we look at these components, I essentially have then the x component, the y component, and again, something that I'll kind of point out a little bit later is that if I want to give these values, so if I want to say that this horizontal component was 4 and this vertical component was 3, as long as we're starting at the origin, notice that this vector, which could be described as 4, 3, notice with the exaggerated inequality signs, it kind of resembles essentially a vector symbol. That 4, 3 is also describing what this terminal point is. This is also the point 4, 3. And so many times when we're dealing with vectors that are always starting at the origin, which we will because of certain rules and axioms and definitions, this will occur. If you're curious about the notation that I was using for the component form, you'll either see these exaggerated inequality symbols, which is probably not proper, or you'll see it look more in terms of parentheses. But we need to be very, very careful that I'm not just describing the ordered point here, but I'm really talking about the vector itself, the arrow, the distance between the initial point to the terminal point 4, 3, the angle, which is its direction, that's getting created here. If you're familiar with polar coordinates, etc. That's a notation that will come up when we start getting into notations with vectors. Now, a vector does not have to live in just a 2D world. You'll notice two-dimensional, so 2D. Anytime you're drawing on a board, anytime you're drawing on your paper, if you are taking notes as you follow along and you're writing down, you are living in a world that is only defined as length and width. One of the things that again, you should be able to experience is three-dimensional, because we are three-dimensional beings, and I'm kind of looking at, I'm in a four-walled room currently, and if you are as well, if you look at the corner of your room, you'll notice that you don't just have two axes breaking out of that. Essentially, you can think about the floor, the corner that's being created as your X and Y axis. You have a third dimension that gets created, creating 3 dimensions, and typically refer to that as height, but if I'm thinking visually, we can describe that in terms of the Z-axis. And again, drawing 3 dimensions in a 2D plane can be kind of challenging. You can kind of think about it like this. I have an X-axis, a Y-axis. This is sitting flat with my Z-axis now coming off of the floor. It's coming off of your paper. It's coming off of your table. And what that now allows is, instead of my 4, 3 vector living here, so imagine this vector that I drew here is the same as this one. It's just now laying flat. Say if, again, you drew this on your paper at home or wherever you are, that not only is it sitting flat, I can now take that vector and raise it off of the table. So again, I think I left this in view. If this is now the vector, I can now lift this off the table. I can now go through the table if I want to, just by now introducing a new dimension. Well, we're no longer now working in a 2-dimensional plane. We're working now in a 3-dimensional plane. And that means my vector can't be described with just 2 components. We can now describe it with 3. And so, as an example, let's say we raised this here. We've now taken it directly up. Think about this as forming a right angle here. We've now created a third vector, which can be described, I'll use a W instead of a V now, using 3 pieces, a WX, a WY, and a WZ, just to be consistent. And again, as long as we're starting at the origin, I can either use the kind of exaggerated vector notation there, inequalities, or I can actually use parentheses, as long as we're assuming that it's starting there at the origin. Notice again that 2-dimensionals references R2. If I'm in 3 dimensions, we notice I can note that here. Now, these are, again, assuming you've got some knowledge of set notations and how this is the set of real numbers. This would be the set of real numbers in 3 dimensions. We could also work in the integers, which is a Z. We can work in the complex numbers, which is a C. Or we can work with natural numbers, essentially just whole numbers, just without including 0, which is an N. A lot of times, if you take a logic class, which I think again is another class that discrete mathematics, which is getting more popular with the amount of computer programmers that are in data scientist roles that are opening up, you'll see more times the Z referencing again integers, but you'll see non-negative integers, so you'll see plus signs, etc. So there's a lot of different set notation I would encourage you to check out if you're interested. But really what I want to ultimately kind of show you with this and kind of end this part of the video with, because I've already talked too long, is that if we continue to increase the dimensions, it gets harder and harder to sketch. And I think it gets harder and harder to kind of physically think about, because our brains really can't go past the 3rd dimension. You start getting into some astrophysicists and things that are way outside of my understanding, physically speaking, where we can go into 4 dimensions, we can go into 5, we can go all the way out to n. And when we are working in our class, a lot of the times we're trying to extend 2 dimensions, 3 dimensions into n dimensions, improving certain theorems and postulates and conjectures work for any space that we are in. And so when we are working in something that is in Rn, we are dealing with vectors that essentially have n components. And because we do not know how many components we have, and we only have so many letters in the English alphabet, we kind of don't use this notation outside of physics and some of the natural sciences. We more so start to use whatever the letter the vector is with some kind of sub index of 1, 2, 3, and in this case all the way out to n. And so this is how you're going to see it defined in the class. This is what the notation that I'm going to use. Again, sometimes you'll kind of see parentheses when we are starting at 0 in the origin. And so this would be a vector that is in dimensional space. If we collect all the possible vectors, we are fulfilling this space. And that kind of rounds out the definition. So hopefully this kind of helps identify what a vector is, at least what it can represent, and some of the key terms that can be used. Next video, if you need to check it out, I would encourage you. We're going to look at vector representations. We've talked about one already, but there's a couple of other ways that vectors can be notated, a couple other ways that you may have seen vectors notated that I want to review. And then I'll talk about the next piece after that.